Okay, students, I want to explain this exercise about the application of the exponential functions. In this case, we have a problem where they are talking about a population of fish that is decreasing exponentially, following the exponential equation a equals a sub 0 times e to the power of kt. So what happens in this case? They say that the population 9 years ago was 1,500. They say that today only 1,000 of the fish are alive. So they say once the population drops below 100, the situation, will be irreversible. So when will this happen according to the model? So they say round to the nearest whole number. So first, we have to understand what is the information they give us. They give us what happened, what was the scenario 9 years ago. 9 years ago, so time is 9. We had an initial population of 1,500. You know, after those 9 years, the actual population is 1,000, right? So 9 years ago was 1,500. This is h sub 0. This is the initial amount, right? And 1,000 is the number of fish that we have at this instant after 9 years. So they give you basically a sub 0, the initial population, the time, 9 years, and the actual population we have after the 9 years. So with all this information, we can find the constant k, right? We know that as there is a decay here because it's decreasing exponentially, we're expecting to have a value of k that would be negative, right? Because it's decreasing. So what are we doing? We say, okay, I will, in this case, of course, let me do something. They say, of course, we're going to substitute a by 1,000 equals a sub 0, that is 1,500, times e to the power of k. K is unknown, and t is just 9 years, right? So what do? You're going to, in this case, first divide by 1,500 both sides, so you get 1,000 over 1,500. This is the same that 2/3, okay? So you have 2/3 equals e to the power of 9k. Here what you have is an exponential equation with different bases, so you're going to apply logarithms to solve this exponential equation. When you apply logarithm to both sides, you have now the natural logarithm of 2/3 is equal to the natural logarithm of e to the power of 9k. Why I use natural logarithm? Because I have e to the power of 9k. A natural logarithm is a logarithm base e, right? This is the same that a logarithm base e, and I know that the natural logarithm of e will be 1. But also I know the property of logarithm, that is the power as a product rule, that say that if I have the logarithm in base b of x to the p, this is p times the logarithm in base b of x. So I can just bring this 9k to the front, and then natural logarithm of e is 1, so what I get is just 9k. So I have natural logarithm of third equals 9k. I divide now both sides by 9, right? I have natural logarithm of 2/3 divided by 9 equals k. And when I substitute that in my calculator, I get that k is equal to negative 0.0451. With this value of k now, I have, my model. There is a equals a sub 0 times e to the power of negative 0.0451 t, right? And what happens, they say in the second part of the problem that once the population drops below 1,000, the situation will be irreversible. So they ask you when will this happen, according to this model. So we have the same tendency, we have the same trend for the next years. So when is that the population will be below 100 fish. So what happened here is now we have that the initial population is 1,000. This is what we have actually at this time. 100 is the value that we're going to have several years from now. So we want to know exactly how many years from now we're going to have those 100 specimens. And then we have here e to the power of negative 0.041451t. So what I'm doing, I am dividing by 1,000 on both sides. So I get 100 over 1,000 equals e to the power of negative 0.041451t. 100 over 1,000 is 0.1 equals e to the power of negative 0.0451t. I will apply again natural logarithm to both sides to do exactly the same thing that I did every time, but in this case, instead of solving for k, I will be solving for t. So I'm going to say 0.1 equals e to the power of negative 0.0451t. If I apply natural logarithm, now I have natural logarithm of 0.1 equals natural logarithm of e to the power of negative 0.0451t. Of course, we bring this exponent as a factor, so we can get here natural logarithm of 0.1 equals negative 0.041t 451t, sorry, times the natural logarithm of e. This is one we know. So now we have, negative 0.0451t in the right side. I will divide by this negative 0.0451 to isolate t right here. So I get natural logarithm of 0.1 divided by negative 0.0451. The natural logarithm of a number between 0 and 1 is negative, so I'm expecting to have a negative number here, and negative over negative is going to be positive. It makes sense because the time have to be positive, right? Don't make sense a negative time. So when you evaluate in your calculator this operation, natural logarithm of 0.1 divided by negative 0.0451, that would be equal to 51.06 years. They say round to the nearest whole number. When they say round to the nearest whole number, you round to the nearest whole year, sorry, you round to 51 year, and that would be in this case the correct answer. So what it means that uh, in 51 years, if we have the same trend, right, if the tendency doesn't change, right, in 51 years, we're going to be facing this scenario where those 1,000 fishes we had, uh, have been, that number have been decreasing during these 51 years, and we have just basically no more than 100 specimens, right? And now the decay of the population is irreversible, and eventually, those fish are not going to be living in the lake anymore, right? We're not going to find any fish, eventually. But in 51 years, we're going to have, following this same tendency, just 100 fishes only. So this is how you solve this exercise. It's very interesting. Basically, all the exponential models are solved in more or less the same way, right? So that's why I'm sharing in this example. So thank you for your attention.